So we're looking at this sheet here. We're talking about synthesis reactions and how many different kinds there are. And then right now we're looking at decomposition. I had not started the thing. So anyway, when you take mercury oxide and you heat it with the sunlight, what would it break down into?
Any? I don't know.
Take a look at it. Right here.
Break down to mercury and oxygen.
And what?
2O.
And mercury. This is mercury.
Yeah, that's what I said.
And oxygen, right?
Yeah.
So in one case, Lavoisier was looking for the gas. He was looking for the gas that was given off, and then that's when he used that to make oxygen gas to do some of the experiments. Now, this stuff here, the stuff that mercury oxide, looks like red. It's like a red powder. You would never think that remember you know what mercury looks like silvery liquid? You would never think you could get mercury out of something that looks like a red powder. But if you break the bonds, and that's what they did, heat was enough to break the bonds. Okay, let's do another one. What about carbonates? What if you have carbonates? In this case, what do you think I could get out of that? What if I wanted to produce CO2? Then I could do that. Here's a hydrogen carbonate. What happens if you get a hydrogen carbonate? You can produce water and CO2. What about this sodium hydroxide? What if you take a hydroxide and you heat it? Again, you're going to form water. Here's one. The one I'm going to show you, we did this one in 10th grade. We actually took hydrogen peroxide and used a catalyst. And it was called manganese dioxide. But the catalyst broke down the hydrogen peroxide. What were those bubbles made out of? And they were made of oxygen, weren't they? So if you wanted to produce oxygen gas, you could do something like this, which is a little dangerous. Heating mercury would be dangerous. Heat it too much, you get mercury vapors, and that's always bad for living things. This is a pretty easy way to produce oxygen gas. And I want to show you one more. Do they have one called chlorates? Do we see it on here? Are chlorates on here anywhere? Oh, I'm not seeing it. Okay. Have you ever seen model rockets? These little engines. You could light them and think, well, it'll get enough oxygen from the air to burn that fuel. But what if you want to make a solid fuel rocket like NASA? Are they going to just simply say, I think there'll be enough oxygen to come in here to burn? No. So what do they use? I don't know why I don't see it here. Do you see carbonate anywhere? Okay, not carbonate, I mean chlorate. Do you see chlorate anywhere?
It's on E.
Oh, here it is. Sorry, I missed it. Take a look at this right here. Yeah, E, thank you. You could take chlorate to the moon. And you can say, well, I need some oxygen to burn for a fire. Well, there is no oxygen. There's no atmosphere on the moon. But what could you take? What if you had this material here? If you heat it, what do you get? Oxygen. So if you're looking for oxygen to burn something else, you could break down something like a chlorate. All right, we talked about this yesterday. Singular placement. You could have a metal kicking out a metal, or you could have a non-metal kicking out a non-metal, couldn't you? And then here's some acids. We'll get to this later, but did you know that a lot of metals, when you put them in hydrochloric acid, they will form this. When you guys in the 10th grade, you did zinc. You put zinc in hydrochloric acid and you had bubbles. And then you put them in a test tube and you lit it and it goes pop. Remember that, the pop test? Remember the pop test? Yeah.
Wait, so why would you bring the metallic chlorate to the moon instead of just bringing oxygen?
Well, you could. Oxygen in the form of a gas would take up a lot of space. So you could, even though you could compress the gas and cool it, pure oxygen. Now, there is a danger with pure oxygen. If it leaks or whatever, then any kind of spark, it would consume almost everything there. So I think it'd be safer. That's a great question. I think it'd be safer to have it here. And also, if you want to use it for a rocket, you can simply mix that powder with the fuel, and then once it gets hot enough, it'll produce the oxygen. You don't have to have a separate source of oxygen there. That's a great question. Now, Here, zinc and hydrochloric acid does make hydrogen gas and do the pop test. But there's you'll find out later, there's a list, and chemistry has a list for everything. They have a list of acids that if you're below this line, then you're capable of kicking hydrogen out of an acid. But there are other metals that do not. See, copper in hydrochloric acid, nothing. Gold in hydrochloric acid, nothing. So there's certain metals that don't react with acids, and they have no ability to kick the hydrogen out, but a lot of them do. And so zinc does, magnesium does, and there's actually a list of which acids are capable of knocking hydrogen out of acids. All right, and the last one, double replacement. We'll spend a little time of this also. Remember, we talked about this thing called driving forces. Driving force. Take a look at this one. Why would this reaction want to take place? What is that makes it want to go? They say go to the right. What makes a reaction want to go to the right? It has to be a thing called a driving force. Okay, so what's the driving force here? And it's the formation of a solid. Anybody remember any other driving forces? The formation of a solid can make the reaction want to go. Sometimes you put two chemicals together, nothing happens. Nothing. There's no reaction. And yet here, there was a driving force, a formation of a solid. See, these were aqueous. These are two solutions, and all of a sudden you get a solid. And that's a precipitate, isn't it? And we'll do a precipitation reaction in here. What's another driving force? Formation of a gas. These two react because a gas is going to be produced as one of the products, and that's a driving force. So here, we studied that before, precipitation. That's where we use that chart. Remember, soluble, insoluble. We'll do that. This is where you use a net ionic equation. I think somebody asked me about that yesterday. We'll do that. This one also is the driving force is the formation of water. Now, every time you have an acid and a base, it's called acid-base neutralization. What is it that makes those ions, what makes them want to react? And it's this real stable compound called water, the formation of water. That drives the reaction to take place, like that. Okay, and last but not least, the combustion reaction, you have some kind of fuel, usually it's a hydrocarbon, sometimes you'll have oxygen in there, and you're going to burn it. This is burning in chemistry. And if it's complete combustion, you get carbon dioxide and water. If it's incomplete, we talked about you might get pure soot. There's a nanoparticle called C2. I just read an article a couple years ago. It said they just recently discovered that in a candle flame, that they actually found another nanoparticle called the buckyball. And the buckyball is that model that, I don't know if I see it, where is it? Yeah. There it is, over there. A soccer ball looking thing that is 60 carbon atoms that look like they're in a geodesic dome. The Buckminster Fuller, he was an architect. He was the one who actually developed the geodesic dome. And so the scientists, instead of naming it after another scientist, they named it after an architect, and they called it a Buckminster Fullerene. Nobody likes to say that, so they call it a buckyball. So anyway, they recently found out that even in a candle flame, there's some nanoparticles, C2, C60, and then the bad stuff for incomplete combustion would be carbon monoxide, okay? My car is famous for being incomplete combustion. Does it give off a lot of water and carbon dioxide? Yeah. Does it give off soot? Yeah. And does it give off carbon monoxide? Yeah, it does. Okay, you okay with that? All right, let's go over and let's talk about the trick, and then I'll have you come up to the camera. All right, let's take a look. And the first thing I notice, let's do trick number one. Trick number one, I'm going to call it the odd-even imbalance or odd-even problem. When I scan here, I notice that this is O2 and this is O3. And you're never going to get an even number to equal an odd number. So the smallest number they both go into is 6. 3 times 2 is 6. 2 times 3 is 6. That's called the odd-even mismatch. Everybody okay on that? All right, trick number 2. Let's go down here. If the polyatomic ion stays the polyatomic ion, then it's probably going to be easier to balance by, see this? That's 1 sulfate. And how many's here? How many sulfates are over here? 3. So let's put a 3 there, okay? That gives me 3 coppers. But how many aluminums do we have? There we go. See that? So trick number 2, if the polyatomic ion stays the polyatomic ion, just treat it like a single atom. And you can, and usually if I balance those first, it works out pretty well. All right, trick number 3. If you see water on one side of the arrow and a hydroxide on the other side, not always, but most of the time, if you'll write the water as HOH, it's easier to classify and it's easier to balance. Okay, that's trick number 3. Trick number 4. Let's see. Let's go with combustion. In a combustion reaction dealing with just a hydrocarbon, they can sometimes be very easy. Sometimes they can be the most difficult. And they can also have some of the biggest numbers I've ever seen. Very rarely do you get above 7 in most chemical reactions as far as coefficients. But if you do, it's going to be a combustion reaction. And the trick there is, as you're going through here, if it looks like you need to put an odd number in front of the water, don't do that. If you put an odd number in front of that water, it will never balance. So you double it. And once you do that, all of a sudden, it makes it pretty easy to balance. Okay, that might be about it. Don't forget, if it's already balanced, you do have to write the word balanced. And we never write the coefficient 1. It is there. There really is. I'll give away one of the, it's not a trick question, but it is. Ready? Multiple choice. What is the sum of all the coefficients of this balanced equation? They make you balance the equation, and they ask you for the sum of the coefficients. What would you say the sum of the coefficients were for this one? 4. But some of you, what if they put 0? Some of you put 0. What's the sum of the coefficients in this one? What's the sum of the coefficients in this one? 5. But what if the multiple choice answer has 1? Or, 2,
We won't put it.
Okay, thank you. Now, I didn't write that question, the author did, but they're just to make sure that, just like your math teacher, when you say X, what's the coefficient? It has a coefficient, doesn't it? 1, right? All right, well, let's go, whoops. These are your groups for later. Okay. All right, is everybody ready? What I'd like you to do then is, I'm going to have you come up here, and we're going to save number 7, but everybody else is going to pick one. So, you want to be first or not?
I would love to.
Okay, good. You get to pick any one you want, and then you get to kind of teach it to us, and just talk it out and say, you know what, when I scan this, here's what I notice. Do you have your pen? You have a pencil with you? Or pen? All right, and Jeff, you're on deck, okay? And you get to pick any one you want.
Good.
Which one do you want?
I'm gonna take
Take 7.
we're gonna
7
save
is
that one. We're gonna do
you
it
weren't
last.
listening clearly.
Wait, listen.
So
All right, so let's see if we can pick up the pace a little bit. You're the teacher, okay? But Jeff, you're gonna be next.
so this is a decomposition. Do I write that over here? I'm gonna do number 9.
Hey, we can't see that.
Okay,
Oh, I'm so sorry.
so you're gonna classify it, and then you're gonna balance it.
So it's a decomposition
Okay, what makes you think that, though? You're trying to teach me something. How do you know the decomposition?
because you start with one thing and you end with 2. So clearly
Right.
there's a
Very
breaking
good.
apart going
Very
on here.
good.
So you got 3 oxygens over here and only 2 over here. So you're gonna need a 3 here and a 2 here to balance that out. And that means you're gonna need a 2 here because then you'll have 2 Ks, 2 CLs, and 6 oxygen, and then you'll have 2 Ks, 2 CLs, and 6 oxygen.
Okay, one more thing. You always go back and see if it can be reduced. Can this be reduced?
No, sir, because
Excellent.
2 and
Excellent. All right, next, go. Woo, very good. I love hearing you guys teach it. That's the better part of this, right?
Oh, yeah.
What do you want to do, Jeff?
10.
Okay, talk to us.
All right, so I'm gonna explain this. So it's a single replacement because there's one, standalone, and then there's the HCl, and then it swaps out. So
Who's kicking out who?
it appears that the hydrogen is getting kicked out, and magnesium is replacing it.
Hydrogen's already in a compound, so why would it kick out anybody?
What do you mean?
Hydrogen's already in a compound, HCl, so how is it gonna kick somebody out?
Oh, it's getting hydrogen is the one getting
So
kicked
who's
out.
kicking
Yeah.
hydrogen out?
CL.
Because that's chlorine. Is the word.
No, hydrogen is combined with chlorine, but somebody's
Yeah.
gonna kick hydrogen out.
Yeah.
Who?
CL.
No.
No,
Chlorine. Chlorine.
okay. Who's kicking hydrogen out? You got a
Well,
choice.
magnesium.
That's it.
If you want to.
So magnesium kicks hydrogen out, and magnesium forms a compound with chlorine, right?
Yes.
But last chapter you learned, how does magnesium form a compound with chlorine? What's the formula?
The formula.
What's the formula for
The
magnesium
secret
chloride?
formula.
And, that's why you're going up here. We're trying to figure out any little holes in your thinking, or what's the formula for magnesium chloride?
What do you mean?
Okay, it's down there, so on the far right, it's one of the products.
Oh, it's single replacement. Yeah, but SR.
No, the question is, what's the formula for magnesium chloride?
Like the written
Yeah.
formula? Oh, the written formula.
Or you can verbalize it.
Oh.
You see MgCl2?
Yeah.
What's the name of that? MgCl2? That's magnesium chloride.
Oh, I knew it.
Now, can I
Oh,
tell you
that
something?
was.
When magnesium kicks out the hydrogen, you can't just lay Mg next to Cl, can you? You still have to know the rules for writing compounds, don't you?
Yeah.
All right, so go ahead, tell me how you balance it now.
All right. So as you see in the products, there's two chlorine,
Oh.
and over here there's only one. So got to
Okay.
put a 2 there. That makes it also 2 hydrogen, which balances out.
Okay.
And the whole time there's just 1 magnesium.
Why do you think they wrote H2 as one of the products? Why didn't they write H?
Because it's a diatomic atom.
Very good, very good. Okay, next. All right, here we go.
Oh.
So, number one
Okay,
is synthesis,
what makes you say that?
because
Synthesis.
I spell it wrong. Because A plus B equals AB.
Okay,
And so that says 2 and that says 3. So if we put that will have to have a 2 up here because that's a 2 and that's a 3. So then that means 2 times 3 equals 6. So I'll put 3 right there, so that'll equal 6. And I'll put 4 over here, so that equals 4.
can this be reduced?
No.
Okay, very good. All right, remember, if any of the reactions or products have a coefficient of 1, you certainly cannot reduce it, can you? All right, next. Clay.
Use.
Which one are you gonna do, Clay?
I don't know. I'll look.
Okay. And I like that. You said, I think I'll pick one and see what happens.
Pick 7.
Can I pick 7?
No.
What now? Oh, not yet.
I don't think I
7
can.
minutes.
Why
don't you do 3?
Should I do 3 or 5?
You should do all the above.
I think it's
Let's do 5 and tell me what trick you're looking at.
Let's do 5. Okay, looks like
How
a
do you
double
classify it?
replacement reaction to me.
It's a what kind?
Double replacement,
Okay.
and that is because I see 2 different
'cause there's double.
compounds that are just switching their
And
cation.
each compound is made of two parts, right?
Yes.
Ions?
Yes. Okay. So let's go ahead and write that on in there. Okay.
It's a little slanted.
Oh, might be. Okay.
Okay, how do you
Then
balance
just twist
So-
the end.
What you're gonna do is make sure that there's the same amount of thingies on both sides. So you got two NO3s over here, which means you gotta have two NO3s over here. So then you gotta give that a coefficient of 2. But now you have two Ks, but you also have two Ks over here. So that's good. You also have one CO4 over here, one over here, one PB over here, one PB over here. But we also have to check the charges to make sure they line up. So,
In this case, though, because the author wrote out all the formulas for you,
we don't have to check the charges?
you
Awesome.
don't have to worry about this.
But check it just in case.
Cool.
The
All right,
authors are
go,
wrong.
next.
Let's
Let's see if we can hurry a little bit, okay? I'm gonna get to some other, couple more. And, Marie, why don't you come up here so we don't have to wait long between people?
Tell them, you should have thought
All
of
right,
that.
what are you gonna do, Lang?
Go, 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 go.
I'll just go with.
Good.
I'll just go with 2, and that's it.
By the way, and the one Clay did, the trick was that he looked at polyatomic ions and treated them as a single thing. Which one are you doing?
2.
Okay,
Yeah, so that's a decomposition,
okay.
and we have 2 oxygen because it's a diatomic element, and so we need 2 over here. So we'll put a 2 up there, and then we need a 2 here because there's 2 over there.
Did you reduce it though?
No, you can't reduce that.
All right, but there's a one in front of you too.
Yes.
Very good. Next. Next.
Someone's gonna get one that they're gonna have to
Oh, I'm
reduce.
Which one do you want to do?
I'll do 4.
Are you sure about that?
Yeah. Okay, so this one is synthesis. And then, so we have the even odd mismatch with the oxygen, so put a 2 here and a 3, and then that means we have to have 4 irons.
Can you reduce it?
No.
Okay, all right, thank you. Very
Sure.
good. Next.
Are you sure you can't?
Oh, boy.
What are you gonna do?
Don't pick the wrong one.
I don't want to do number
You can
3.
do it.
Do
Okay.
Now, I'll show you a trick. I'll show you a trick.
Okay.
Number
You
3,
don't got that.
there's a hydroxide on the left.
So we're gonna write this as
Yeah, let's do
HOH.
that. Now, I think it'll make, watch what happens here now.
Okay, it's a double replacement.
See?
I could have written DR. And then, okay, so to balance it, should I start with the hydroxide group?
Yeah.
Okay.
Do that.
Well, there's one OH over here, and there's still only one over
Yes.
here.
That's right.
So we can leave that. But then there's 2 hydrogens
They're
here.
not in hydroxide.
Yes, so we have to have 2 that are not in hydroxide over here.
Very good.
Ah.
Oh.
And then,
That gives you how many hydroxides?
that gives me 2 hydroxides, which means we gotta make this 2.
Already did it.
Very nice.
And then there's already 2 sodiums over here, and there's 1 sulfate group.
See? So I'm glad you did that one, okay?
Wow.
All right, let's take a look at the number 6. Let's take a look at number 6. There's an uneven mismatch. If you see H2 and H3.
Would you like me to go back up
So that was a
next
pretty
one?
simple one to do. Now, even though
Oh, I think Clay should do it.
we didn't have any combustion, on this side here. This is kind of easy. Like I said, here's a mismatch 3 and 2. So like that. Yeah. So that was pretty. How would you classify this one? Okay, synthesis. Okay, and then here, how would you classify this one? I'm trying to save a little bit of time here. How would you classify this one? Number 8.
Replacement right there.
Okay, so the metal kicks out the metal, doesn't it? Now, in this case, we have 1 iron, and what do we have there right here? Well, first of all, it's single replacement, but I have to write the word what? Balanced. It's already balanced, so I don't have to add anything. Now also, even though I showed you some tricks on how to balance equations, take a look at number 7, and I want everybody to try it. And you can try all the different tricks you want, but sometimes it just takes persistence. All right, let's see who the first person can get number 7. Oh, you already have it? All right, don't say anything then. Wow, that's fast. Everybody, try number 7, okay? Try number 7. Parker, try number 7. All right. You can't get frustrated. You have to sometimes be a little patient. Now, the first thing I notice is that my nitrates don't stay as nitrates. That means sometimes that means trouble. Okay, because my nitrates broke down.
It's that final O2.
So that's going to make it a little
tricky
trick.
bit,
That makes it a little trickier, doesn't it?
Yeah.
So let's give everybody a chance to try it. Okay, we're gonna have to leave. Sorry. I'll tell you what. We have to leave. We gotta go to chapel. So I don't want you to get there too late. Go ahead. Let's go ahead and get your stuff, and let's go ahead and leave today. So we have to go to chapel.